Okay, cool. All right, Will's here. We can get started. What's for lunch today? Nice. It looks like a giant peanut butter and jelly sandwich, but really it's a crepe. Okay, we're good. There's some weird stuff happening with my monitor here, but this looks good, so I'm going to run with it. Okay, so here's what we're going to do today. We're going to spend a little bit of time talking about monitors. That'll be really fast. And then we're going to spend most of the day talking about juggling the pipeline. So talking about, well, we've talked about this fixed function pipeline for all these weeks and talked about how to implement things internally. And I think one of the really exciting things that hopefully you've got out of the guest speakers is, and certainly you'll be getting on Thursday when Jeremy comes and speaks. Jeremy's coming from Stanford, and he's done a system called GRAMPS. And it's sort of looking at what should the programming model look like when you have a programmable pipeline. So I'm really looking forward to that because I haven't seen this talk before. But if we did have a programmable pipeline, what are some of the things that you'd like to be able to do with it? So we sort of looked a little bit about, okay, well, you could completely change the pipeline and do ray tracing instead. But if we want to do a polygonal pipeline, but we want to add different kinds of stages or functionality, what would those be? So I've got some cool examples, which will be fun. Okay, we'll spend a little bit of time on monitors since we didn't get to that last time. Okay, so you have, this is kind of cool because you have a brightness knob on your monitor. What does that actually mean? All right, so if you're driving a CRT, not a flat panel, but a CRT, it ends up having a nonlinear response to the input signal, right? So the signal is voltage, right? You have some place between 0 and 255 in your frame buffer, and then you need to turn that into a certain amount of voltage, and that's what's going to set. So usually there's some sort of linear mapping going on there. All right, so you put in your voltage, the brightness knob sort of biases the voltage, and then you take that to the gamma power, and that spits out a certain number of electrons. That's sort of your intensity. Okay, so the intensity is actually the number of number of photons that it's spitting out. Okay, so that's nonlinear. So that's a little bit of a problem. Right? Because what you want is to, if you go from 50 in your frame buffer to 100 in your frame buffer, you want it to spit out twice as many photons, but it doesn't work like that. CRTs just don't work like that. Okay. Now, we have another problem, which is that our eye has a nonlinear response to intensity. So if I spit out 50 photons at your eye and I spit out 100 photons at your eye, it'd be nice if you perceived that as being twice as bright, but you don't. Okay? Instead, you perceive brightness as the 0.4th power of intensity. Right? So that's kind of a problem, too. But one of the very fortunate things that sort of worked out is that this nonlinearity of your monitor, which is called gamma, and this perceived brightness issue that's in your psychophysical system end up sort of multiplying out and having this totally flat response. And that is a very, very fortunate lucky thing. So here's sort of your graph version of this. Okay? Here's what you have in your frame buffer here, okay? And here's how many photons it ends up spitting out, how intense it is. So notice it's this nonlinear sort of curve here, and that's bad. But this is what you actually perceive as brightness against the frame buffer value. And that is very, very good, okay? So these two horrible nonlinearities totally crunch each other out, and you get this nice linear curve between what you put in your frame buffer and how bright you perceive it is. So everybody's really happy with this. This is really cool. So when we talk about gamma correction, we are actually talking about this gamma thing here. Okay? If you're able to control the gamma, then that's called gamma correction, and you can change this gamma. And what it's going to do is it's going to change this sort of response curve here. All right? So when you do that in your control panel, that's what you actually end up changing. So we have two choices. We can either store the image linear in brightness, which is the right thing over there, or we can store it linear intensity, which is the left curve over here. So we perceive brightness. It makes sense to do it from the point of view of storage precision. It turns out, as people, I think I had this on the last slide. What we actually perceive is, no, I don't have that anywhere. Well, we can perceive a difference of roughly 1%. All right? So if you have two values and one's at 1 and one's 1.01, we can perceive that difference. We can't perceive 1 versus 1.005, but we can perceive 1% or more. So theoretically, if we assigned our values correctly, we would only need 100. We would only need 100 different gradations there, okay? Because it's only 1% difference is going to change. Okay. So if we store it linear in brightness, it's nice because then we can divide up. We only need 100. We can divide it up into 256 even bins, and it would work correctly. But it turns out this means every time we do a pixel operation, we have to do conversion. And the reason we want to think about it this way is because if I have a red photon or like 100 red photons and 100 blue photons, we'd want to add them up and get 100 purple photons or 200 purple photons. But that would only work if it was linear intensity. Okay, because intensity is sort of measuring photons. Brightness is measuring our perception of photons, and so there's this nonlinearity there. So nobody ends up doing this. Instead, we store at linear intensity. Basically, your frame buffer is capturing how many photons are there. Okay, that's how actual intensity actually is. So it means that you do conversion during display. This is your gamma correction sort of thing. One of the issues is because of the nonlinearity we have there, there's big brightness steps at low intensities. If you look at your frame buffer, it has the value 1 and the value 2, and you look at two things next to each other, you can totally tell there's a difference there. So it means that 8 bits really aren't quite enough. And ideally, if we had monitors that could have more gradations at the low end, we would really benefit from that. But as it is, you're going to see some banding. But the math for this ends up working much, much better because you're adding up photons. So anyway, this is the direction that we really want to go. Other trends I wanted to note. One is that display resolution is changing over time, but it's changing really slowly. So when we look at technology trends and we look at how quickly like our memory bandwidth is increasing and how quickly compute is increasing and so on, we're going up roughly 10% a year in terms of what the biggest, craziest monitor is. This is one that came out in 2001. I actually have a picture of that. It's this Bertha. It's totally awesome display. Like, it's really cool because you can't even tell there's pixels. They're so small. But I don't know any monitors today that are even better than that. Okay, has anybody seen a monitor that's better than that? Not necessarily bigger, but like, I mean, this is only a 22-inch diagonal. So that's not particularly big. But having 3K by 2K is really just a wicked big monitor. So the moral of the story is that this is going up so slowly that you can pretty much ignore it. Right? Monitors aren't really getting too much bigger. Pixar film, I hear, is roughly 4 by 3, 4,000 by 3,000 pixels. That's good enough for film. It's good enough for Pixar. It's probably good enough for anybody. Okay. Another trend that's kind of interesting is this trend toward using high dynamic range images. And this is something that's new over just the last few years in games. And the issue is that if we have a frame buffer and it's got 8 bits per channel, we want to represent something that has a very large dynamic range, from very bright to very light, the frame buffer does a very bad job of that. The human eye can detect 10 orders of magnitude. So that's like, you're trapped in a dark cave versus you stare at the sun. There's like 10 orders of magnitude difference in terms of actual intensity, the number of photons that are hitting your eye. And we can actually detect this, and we're really good at it. A monitor can do roughly 2 orders of magnitude. It can do like 100 times as bright, and that's about it. And you can buy really expensive monitors that will give you like 1,000 times as bright. Okay? But it's nothing near the real world. So the problem is when you have a picture like this, and you have really dark regions and really light regions, you sort of have this choice of either here we're just looking at the dark regions, and here we're just looking at the light regions. But just in a normal frame buffer, you're doing a very bad job of being able to represent both the very light regions and the very dark regions. And so what you want to do is figure out how to take the whole gamut, the whole range of light, and map it down into something your frame buffer can have. And so if we look here, you can actually see dark regions and light regions fairly well with these sort of mappings here. And so that's sort of a research problem. The problem is called the tone mapping problem, and being able to do this efficiently is pretty cool. Now I hear modern games are actually using HDR kind of stuff. Is that accurate?
Yes.
Okay. So that's sort of a new thing here. But it means you have a floating point frame buffer, and you have to be able to convert it eventually into something your monitor can do. So that's kind of an interesting technique. Okay, the last thing I wanted to mention was on this issue of special purpose DRAM. So over the years, there's been a number of kinds of DRAM that people have thought up that they say, this would be awesome for graphics. We want this one particular thing to be able to do that we could put this new feature into this DRAM and make it work. And it's going to do this cool stuff. So VRAM, for instance, is really old, and it was in the 1980s. And basically, it was just regular RAM, but it had a serial port sort of out the side where you could trickle out the frame buffer. So it would do like the scan out to your monitor. So that was really cool. This FBRAM, later called 3D RAM, was developed by Sun. And so the big idea here was they said, well, let's say we want to do, I'm right on the board now. Okay, let's say we want to do a frame buffer. We have our GPU, and we have our memory, and we want to do some depth buffer tests. So what we do is we send a request to read the Z buffer. Okay, and then we get back the Z buffer value. And then we do this comparison here to figure out on the GPU, am I closer or farther away from the Z buffer? Let's say I pass the Z buffer test. Then I write my Z in color. Okay? So you say, well, that ends up being a relatively long operation because we have to do three trips to do our Z buffer write. So instead what we're going to do is we're going to have this smart memory here, and it's going to have an ALU on the memory side. And what we're going to do is we're going to write our Z value and our color value to the ALU, and the ALU will say, okay, I'm going to make a decision on the Z value. I'm going to look at my Z value and the new Z value that's coming in, and only if this passes am I going to write the color. So all the smarts are on the side of the memory. So you say, wow, that's great. I mean, it really is a cool technique. It's a smart thing to be able to do. It's really cheap to be able to build that ALU because it's very, very simple and you can build it fast. So there's some logic process issues here and so on, okay? But it's a smart thing to be able to do. So this is an example of what people have tried to do over the years. They've said, we can have smarter RAMs. We can have better RAMs that can do this really thing for graphics. Every one of those attempts have failed. And they fail because no matter what cool things people put in them, the commodity ends up winning. So you can say, well, it's got this great thing, it improves our performance and so on. Yeah, but it costs $50 more. It's cheaper for us to go buy the cheapest DRAM possible and put it in, and the commodity will end up winning. So that's sort of a sad truth. You think of this great technology thing here, but you just can't make it work economically. That DRAM at this point is a commodity market, just like wheat futures or pork bellies or anything like that. And the low cost ends up winning over everything else. Okay, so that was the end of my monitor sort of discussion. Anybody have any questions on compositing? Okay, well, we're going to be spending the rest of the talk toward this issue of juggling the pipeline. So I'm going to start by just sort of generalizing the pipeline a little bit. And this is really one of my favorite diagrams. I think we've looked at it before. And so this is from Pat Hanrahan and Kurt Akeley. And so what they looked at is they said, well, if we take our pipeline and we generalize it, what are sort of the pieces going on here? And the way you want to kind of think about it is that we have two different kinds of sort of kernels that we're running here, two different kinds of operations. One of them are operations on a particular primitive, right? So we have a surface, and we do an operation on every surface, an operation on every vertex, on every primitive, and so on. Okay? So it's sort of you take in something of type X and you output type X. And the other ones of these are ones that convert from type X to type Y. So primitive assembly converts from a list of vertices to a list of primitives and so on. Right? So this is more general than OpenGL. It's more general than the ones that we've looked at. It's basically this big stream processor of either converting from one type to another or processing one type. And you'd like all these types to be able to look into some sort of global memory here. You'd like to be able to move this this transition between object space and image space that currently sort of happens in rasterization and so on. So this is sort of a general picture that we like to move toward.
Why is the boundary between object space and image space in the per vertex box rather than between the per primitive and the rasterization box?
So you would like to be able to have, the important thing is you'd like to be able to move that line. Okay, you'd like to be able to do that conversion in different places if you so choose. Could you do it here? Sure. Could you do it down here? Absolutely.
Why did they choose this decomposition?
I don't know that this was meant to expound any particular place to do it or not. I'd like to think that we could move it, and different interfaces will allow us, different APIs will allow us to do it in different places.
It seems that, and you have vertices and primitives and all that stuff lives in object space, and then at some point your meat grinder, the rasterization box, there spews out fragments, and then you're in image space.
Yep. So, or you could kind of think of, doing it in, you could project them into object space, into image space in the vertex stage. I mean, if you go all the way through projection, that's kind of where you're landed, right?
So, right. So the which coordinate system you're in doesn't seem to be a very good way to characterize image space versus object space. Well,
so usually we're going to next week when we do the lecture on parallelism, this is when we're really going to try to tease this out. What is object parallel and what is image parallel? So the next picture is sort of OpenGL, and there I hope I got the picture right, or they got the picture right. I drew this picture, and I said, well, it's kind of where you project it into image space, and then rasterization is all done completely in object space sort of thing, right? This is the right place to draw it for OpenGL. Probably the right thing for me to do is to go back here and just have this sort of jagged thing is I think, a more realistic way to do it.
Thinking about the infinite reality engine block diagram and that big crossbar switch, they were all about sort middle.
We will talk about that next Tuesday.
All right, I'll shut up.
Okay. All right, so OpenGL is something that we're comfortable with. Right? And so we can look and say, well, OpenGL doesn't do all these things, right? OpenGL doesn't do things per surface or tessellation. It sort of takes the middle part here, right? It doesn't do operations per pixel, or at least not programmable ones. Okay, but this is what we have, and this is how it sort of maps here, and this is the place where it converts from one to the other. And at this point, we have vertex program, geometry program, and fragment program, which is great. We can access texture or global memory for any of those. Okay? But there's other decisions that we could make. And we talked about some alternatives last time, or several lectures ago. We could say, well, right now we do a Z-buffer sort of thing. We're making decisions on visibility very late in the pipeline. Perhaps it might be better to try to cull some work earlier in the pipeline and make some decisions earlier. All right? Where do we do our texturing? Well, historically, OpenGL was just texture last machine. We textured late in the pipeline. Now we texture in 2 different places, actually 3 different places.
I had a question that kind of was from the previous slide. Tessellation, OpenGL not doing it. Isn't it now supposed to be supported by the GPU to do, because it's related to DirectX 10, but they want to be able to do tessellation, so shouldn't OpenGL...
will support tessellation.
Is OpenGL going to move towards that too, probably, to match?
Right. If DX supports it and
OpenGL has to, basically.
The vendors will then release mutually incompatible OpenGL extensions that will then have to be worked out in committee 3 years later.
Okay. So eventually it's kind of like expanding the...
Yeah. And this per the geometry program, right? That's one that didn't exist 2 years ago. Okay. When I gave this talk last time, that said something else. Okay. So, I mean, this isn't static, but it's a point in the design space. Okay, so we can do texturing different places. Where do we do shading? Well, right now we do some vertex shading, some fragment shading, but we aren't doing deferred shading. Okay, it makes sense to say, well, shading is getting more and more expensive. Why don't we try to compute visibility first, and then do our shading after the visibility is computed? And then we're not doing a whole bunch of shading of things that are not visible. So there's good reasons why the current interfaces have picked the decisions that they have, but there are other decisions that they could have made. And so we're going to talk about some ways to extend this today a little bit. So we'll start off here. This is a particular different pipeline. Does anybody know this pipeline? We'll talk about this in some detail.
Is this pixel planes?
It's not pixel planes. Okay, this is Reyes. This is the Pixar rendering pipelines. They've made some different choices. So just to sort of walk through some of the differences here. So it has one programmable stage rather than multiple programmable stages. It does not do rasterization, but instead sampling. It uses micropolygons. We're going to talk about all these things in more detail. Just to sort of sum that up. So OpenGL has different coordinate spaces and different shaders, and you can shade it more places in the pipeline. Reyes only does shading at one stage of the pipeline. OpenGL will rasterize any size triangles. Okay? Instead, Reyes chops up all of its primitives into what is called micropolygons. Each micropolygon is no bigger than the size of a pixel, so they're always bounded. So then you don't have to rasterize them. On the other hand, you do have to chop them up, and that's an expensive thing to be able to do, and that's what Reyes does. So OpenGL doesn't do tessellation. Reyes has to do tessellation to chop things up into micropolygons early.
Is the tessellator program, whatever, programmable, or is it fixed function always does the same thing?
Well, I mean, Reyes is a software pipeline, right? So it's programmable in the sense that it runs on a CPU and it gets, can it take different inputs, different curves and surfaces? Sure. So old Reyes did, particular kinds of patches like a Bezier patch, for instance. Subdivision surfaces are a more recent invention, and that's now been integrated into the Reyes pipeline. Okay. So let's see. I'll just walk. So these are slides from my grad student Anjul, and he presented these at SIGGRAPH Asia in December. And so I've just sort of stolen all these slides without his permission. But sort of to talk about the 4 stages here and what we're trying to do in Reyes and why it's a little bit different. So and what are the interesting research questions here? Right? So if we wanted to do this sort of thing in a real-time pipeline, what would it take for us to be able to do this? So we're going to start off that we're going to bring in surfaces. So some sort of mathematical description of a surface. And we'd like to convert this into these micropolygons. And the micropolygons are going to be very small. They're the size of a pixel. So input is a bunch of higher order surfaces, and we can have those in different sorts of formats. They can also be what are called displacement maps. You describe sort of a smooth surface, and then you have essentially a texture that's over that surface that says how much we're going to displace it. So if you want to draw an orange, for instance, you might have a nice smooth fruit, and then you have a map that's going to show how that fruit becomes bumpy. Okay, so that's a very common way that you do surfaces in something like Reyes. So what do we do then? Okay, we start off having this big surface here, and we need to cut it up into a bunch of little tiny micropolygons. So one thing we could do is we could just say, okay, well, what's the extent here? This is 100 pixels by 100 pixels, so we're just going to divide it into 10,000 different micropolygons. Okay, that's a tractable way to be able to do it. And it turns out that's not a very smart way to be able to do it. Okay, the problem here is that let's say this thing is, where this part is much closer to you and this part is much farther away from you. Well, we'd want to subdivide this part very finely because it's close to you guys. But this part we're going to want to not subdivide finely at all because it's far away. We actually want to do adaptive subdivision here. Okay? We want to subdivide only as much as we have to. And it might be that we're going to take parts of this surface and subdivide it more finely than other parts of this surface. Right? So we start off maybe doing some sort of subdivision that looks a fairly coarse subdivision, and we keep subdividing more and more and more. And it might be that the parts that are closer to you get subdivided more than the parts that are farther apart. And then once we're done, let me go back here, we have bounded quads here that we call grids. And so we've tried to get to a point where roughly every grid is the same size. This requires adaptive subdivision. And then we take that grid and we uniformly tessellate that. So that's something where we just do, okay, subdivide it into an 8 by 8 mesh or a 16 by 16 mesh or something. But it's very important that we have these 2 steps here because otherwise you end up with these ton of these little tiny micropolygons that are really, really small and never actually get rendered. You want to make sure that you have roughly the same number of micropolygons as you do pixels. Okay? Then you're not wasting a lot of work. So you do this for every surface in the whole thing. Okay. So what's really hard here? Okay, so really the research challenges here are issues having, how do you tessellate this thing adaptively, right? So you say, okay, well, do I need to chop that up or not? Well, it's too big. I'm going to chop it into smaller pieces. I'm going to take that guy and chop it into smaller pieces. This sort of lends itself to this depth-first traversal here, and that's something that's very difficult to parallelize. Okay, so that's a hard problem there. The other problem is that one of the nice things about OpenGL is, you can have fairly big triangles, and you have just one triangle structure, and it covers lots of pixels. When you divide everything down into these little tiny micropolygons, okay, that's just an enormous amount of memory. Okay, so it's hard to make that work. Instead, what most Reyes implementations do is they do the same thing Larabee's going to do, which is divide the screen into buckets, and they do one bucket at a time because they can't store the entire scene's worth of micropolygons all in memory at the same time. So that's a big challenge there. Okay, so we end up turning all those into grids and then tessellating them there. So the output of this stage is an unshaded grid. Okay, so now we've got a bunch of grids that generate a bunch of micropolygons, and hopefully every micropolygon is roughly the same size. The nice part about that is that everything in Reyes goes to grids. And if we're going to shade this grid, this parallelizes very, very well. It parallelizes well because this whole grid is going to be shaded. All the micropolygons here are going to be shaded by the same program, right? They're going to have the same shader. And so that ends up subdividing very well, or parallelizing very well. Like you can think of a CUDA block. A block would be a nice match for this, that you're throwing, 8 by 8, maybe 256 micropolygons all at the same shader. So that's going to be very good at parallelizing. If you think about texture access here, right, this texture access is going to be very coalesced as well. So that's Reyes was designed at the start to vectorize nicely. So RenderMan has shaders for every grid. So it has different kinds of shaders. So unlike OpenGL, where you sort of have one shader for each stage, one shader for each stage, here we have separate shaders. You have a shader that just calculates these displacements, the bumpiness. You have a shader that does color on the surface. You have shaders for lights, and then you have volumes between lights. So you run, if this was a smoky room, I would run one thing for my sweater, one thing for that light, and one thing for the smoke in between. So they've sort of factored out the different kinds of shaders that you can run. So, but the nice part is that ends up being very SIMD friendly, and it's very local. So that's a good thing. The challenges are really complex shaders. So if you look at a real Pixar kind of shader, that's something that's tens or hundreds of thousands of lines of code. So it's not something that a GPU could do very well today. It's a ton of code. And then you have things in RenderMan that do global illumination and calculate that. RenderMan shaders can go out to disk, right? And you can have, that's something that really isn't supported in current things. And then they can access this enormous amount of texture. Okay, so a big part of Pixar's problem in running RenderMan efficiently is how do they manage their memory? So they might be accessing hundreds of gigabytes of texture on every frame, and so their memory isn't that big. They have to be very careful about managing that. And so as we move to more complex kind of shaders, these are things we're going to run into as well. Okay, so you're done. You have sort of shaded grids now. You have all these micropolygons. The next stage is sampling. And so we talked about stochastic sampling a little bit, and that's really key to doing RenderMan here. So you've got this big sea of micropolygons here of different colors and so on. And then our job is to sample per pixel and take many samples per pixel. And we talked about different strategies for doing that last week, sort of how do we do sampling. And we talked about, okay, well, do we do supersampling? Do we talk about multi-sampling? We decided one of the good things from the signal processing point of view is doing the stochastic sampling, essentially some sort of random sampling. And so Pixar is very good at this, and this is what they have patents on, and they've been very aggressive about enforcing those patents. But my understanding is most of them have expired at this point. So that's a good thing for future graphics hardware. Then what you're going to have is this issue of at each pixel location, you're going to have many samples. You took all these different samples. And so this is also a real research challenge to deal with, because in current graphics hardware, you pretty much have, you're only keeping one bit of information per pixel. Right? You sort of have your color, your depth information, you have a color, but you're not able to keep many different fragments around at the same time for any given pixel. Instead, every time a new fragment comes in, it gets composited with the old fragment. So this is part of the issue of this order-independent transparency, why it's so hard. You don't have the ability in current GPUs to keep around multiple fragments at the same time and then resolve everything afterwards. But that's something that RenderMan does require, that it does want. So generating the samples is a problem. Okay, so how do we actually generate those? Li Yiwei did some cool work at SIGGRAPH last year that actually generated a Poisson sampling pattern and was able to do that using the GPU in parallel, which is really cool. And so that's potentially a good way for us to be able to take good Poisson samples. good blue noise samples. We have to do all the intersections with the micropolygons, so that's an issue. And then our output here is this list of samples, and sort of the final challenge is how do we put those all together? Okay? You have this sort of structure where how do you store all these samples in, and this is not particularly data parallel because every pixel location might have many different samples. And you have to sort of ram them all together, okay? So run a program at every pixel to composite all these samples, and again, not very parallel friendly because you might have different numbers of samples. And then once you've computed all these samples, you have to run some sort of filtering kernel over them. And your filtering kernel is probably going to be better than just a box filter. You're probably going to care about having a broader extent and doing a better job on the signal processing point of view. So the real challenges here from a research point of view are how do we represent a work list that's irregular, where every pixel has a different amount of work to do. And that's really hard. And so in the CPU world, you can do this sort of with a linked list per sample. It's a very poorly structured thing for a GPU. It's just not very parallel friendly. So it's really an enormous challenge how you store a whole bunch of fragments and associate them with pixels and be able to do this sort of reduction of, okay, well, I'm going to take these things, reduce them to one color, this thing, reduce it to one color, these things, reduce it to one color, and so on. So that's a real challenge. So sort of the easy stuff here is geometry ends up parallelizing fairly well with some recent work. Shading is great. We like shading a lot, and that's going to end up being SIMD friendly, hopefully at least with simple shaders. You get really good locality and textures when you do grid shading. At least we have ways to start doing sampling kinds of stuff, so that's a big plus. But there's a lot of things that are hard. So things that we want to work on that are difficult things in Reyes. So these are sort of unanswered research questions that hopefully people are going to be interested in looking at. Okay, so this is a good time to stop for questions on Reyes.
So it seems this is pretty complicated. Is this that much easier to do than ray tracing, and for the quality?
Well, it's different than ray tracing. I mean, one way you can answer that question is sort of the existence proof, right? Pixar could have used ray tracing for the last 20 years to do its movies, and it's decided that the right thing to do is to do mostly Reyes-style stuff. Now, in recent years, they've added ray tracing to RenderMan because there are effects that are very difficult to do using this sort of pipeline. So I should back up just a little bit and say, and I'm going to come back to this, and say what the neat things about Reyes are. Okay, so one of the neat things about Reyes is the way that they coherently access textures, that when you go on a grid and you texture in object space, that is a very efficient thing to be able to do. One of the things with Reyes that really, that this whole pipeline is really built around is this idea of shading being the most important thing in the pipeline. Okay? So when you're running RenderMan, most of your time is spent doing shaders. Not very much of it is spent doing the other thing, and the reason is because the shaders are really, really complicated. So what you're really trying to avoid in doing complex effects is shading more than once. You only want to shade once per sample. You don't want to have to compute it many times. The kind of effects that they really want to get are things that we don't see on GPUs very much today, and there's two big effects they really like. One is motion blur, and one is depth of field. So motion blur is sort of, you open your camera shutter, and I'm running really fast across it, and then you close your camera shutter. And it looks like, this yellow stripe on my sweater is sort of smeared. And that's the right thing to do from a signal processing point of view. Okay? That we basically integrated over the time the shutter was open. And, this yellow stripe on my sweater sort of gets, it's integrated across that whole time. So when I actually draw the picture, it's going to look like there's a big yellow stripe going across here. Now, what I don't want to do is to color yellow here, color yellow here, color yellow here, and I have to compute shading all the way across here. So Reyes is designed so that we don't have to do that. Reyes is designed so that you compute all the samples, okay, and you color them all and so on. And then the last step, you can sort of distribute what you've already computed across multiple pixels. Okay, so you can sort of smear it, but you only have to sample it once. That's one of the big ideas. The other big idea is for depth of field, it's the same sort of thing. You might have one sample that contributes to many pixels, and again, you try to only shade that sample once, and then use that. Okay, so it's very different than OpenGL. In OpenGL or DirectX, if you want to do those sort of effects, traditionally today, you would have to compute that sample at many, many places just because of the way this thing was designed. Okay, so one of the neat things about the way RenderMan was designed is RenderMan will work with either a ray tracing set of primitives or a rasterization set of primitives like in Reyes. And the fact that it was designed to be able to do both is really a remarkable achievement and why it's been such amazing work. People have built ray tracing renders before. So for a long time, you could use a set of tools called the Blue Moon Rendering Tools, BMRT. And it was an open source ray tracing implementation of RenderMan, which is a really cool thing to be able to do. The problem with ray tracing is that what makes it difficult is that at any ray could potentially intersect any other thing in the entire scene. Okay? And when you're doing complex sort of lighting effects, you've got rays bouncing all over the place. So it makes for very incoherent access. And you have to sort of access geometry all over the place to be able to make it work. Whereas when you're rasterizing a particular triangle, like an OpenGL, you're only looking at that triangle, and you don't have to know about any other triangles in the whole scene. So from a memory and data management point of view, rasterization-based approaches look really good. Asymptotically, ray tracing looks really good in the long run. The question is, how big are those constants in front of the O of whatever term that you're looking at? Today, they're pretty big, and people haven't been able to find a way to get, if you're going to spend this amount of compute, you can make it look better with rasterization than ray tracing.
For the global illumination stuff you were talking about earlier, do you know what techniques they dominantly use historically? I mean, I know you can do like photon mapping,
right.
Or do they like combine a bunch of different techniques and get some kind of composite image?
Yeah, so I don't really know this. I would imagine it's movie dependent on what they end up doing. Like they'll do something different in an underwater Nemo scene than they will in an outdoor scene than they would inside in a room. That's not something I really know very well. Do you know?
I think it's something called final gather, whereas they do the photon map, right? So they shoot a bunch of photons, but then the final gather is evaluated at the very end. So it's not during object space, but it's in image space.
Okay.
It's something around those lines.
I don't really know much about the way that people do global illumination techniques. It's
Right.
not really in the real-time GPU world. So
Because I think, subsurface scattering is considered a global illumination technique, but it's only good for like certain surfaces. So I was wondering.
Scan.
Yeah, and like marble, I think, and some
Marble is
other,
good.
and milk. That was another example I saw.
No, all that's true. That requires that's very well suited for like photon mapping kind of techniques. Again, that I don't know. Photon mapping is basically ray tracing sort of starts at your eye and like bounces around and eventually hits the light. And so photon mapping sort of factors that into your eye sends out a bunch of photons and the light sends out a bunch of photons, and then they sort of meet up with each other and shake hands, and they decide, okay, well, you're going to be in the final image. So that's a pretty glib way of explaining it. But I'm not sure what's actually done in RenderMan in terms of global illumination stuff.
Can each photon be calculated independently of every other photon, and all the data brought together in the end?
Yeah.
That's what they do.
Yeah. And so in that sense, that parallelizes fairly nicely. But on the other hand, every photon, again, has to potentially be able to access the entire scene. So the coherence of access is not as great as you might like. Okay. So that's Reyes, and it's very exciting. And when Jeremy comes on Thursday, he'll certainly be talking about this a little bit. The Stanford group is looking at Reyes pretty heavily. We know that Intel's interested in this, and this is work we've published in as well. So we're also really interested in this topic. So there's some really neat things about this pipeline. It was designed to be vectorized, and there's some effects it's going to have that are going to look really good. Okay. Here's another one. I don't expect that you will know this particular pipeline, but this was a project by an Australian guy named Matt Regan, and he actually built this in hardware, I guess, the early 1990s. And so he had this wire wrap board and all these chips, and went and built the whole thing. It wasn't even with FPGAs. He did the whole thing out of discrete random logic kind of stuff. Amazing thing to be able to do. Crazy guy on the other side of the planet. Comes up with this great cool thing. So the object here is that he wanted to optimize a particular pipeline to minimize the latency. Okay, and what he wanted to minimize was eyeball latency. Okay, we as people can detect latencies up to roughly 10 milliseconds. Right, we can probably get a little bit better than that, but not too much better than that. And the problem today is that we have like double buffering techniques, and everything's really optimized for bandwidth. So when you talk about like how long does it take from the time you move your mouse to the time it actually changes on the screen, there's some noticeable lag in any modern game. Part of it is because you double buffer, right? You double buffer and you have to render the entire scene to the back buffer, and then you have to switch the buffers, and then you have to scan out the buffer. Okay, and you're only going at 100 frames a second, so it's only coming up every 10 milliseconds. So typically the gap between the time you move your mouse and the time the scene actually reaches your eyeballs is 30, 40, 50, 60 nanoseconds. And you can tell that. You can tell that there's lag. So what he wanted to build was something that was the least amount of lag possible, because he thought this would make for a more immersive kind of environment. So here's what he did. He took the entire scene. What he did is he said, well, the problem here is this issue of viewpoint determination. When we determine where your viewpoint is, okay, you move your mouse, there's this long latency to actually rendering the whole scene, putting into the back buffer, and so on. Like there's this big loop between viewport determination and the time you actually get a picture out. So we're going to try to cut that loop. We're going to try to do this in a different way. So here's what we're going to do. We're going to render the entire scene irrespective of where your viewport is. Okay, so what I'm looking at here is a cube map. What that is that I stand here in the middle of this room, and I render everything all the way around me, everything above me, everything below me, and I put it onto a cube. Okay, and that's what I've done here. If you wrap this up, it's a cube. It's everything. It's everything that's potentially visible by me. Okay, so I'm going to do this, I don't want to say ahead of time, but I'm going to do this on my own schedule, and I'm going to render this as fast as I can, but this cube is going to be available. And what this is really optimized for is the case where I stand right here and I move my head a lot. So I'm at this fixed viewpoint location, but I'm moving my head. If that's the case, then this is always going to be valid, and I'm always going to have all the pixels that I need here. And so what the real-time loop here is over here, which is sort of a different thing. So what we're going to do in this loop is sort of a beam chasing kind of technique. Okay? I'm going to determine where my viewpoint is, and I'm drawing this particular pixel here. It'll say, okay, given this pixel, I can do this math very quickly to figure out where I need to look up where that pixel is in this particular drawing here, and I'm going to grab it right before I need it. So it's roughly like it's on the order of a millisecond of latency. But for me to be able to compute this and look it up and bring it back. Okay? And what it means is that this, I'm not having to wait for this whole thing to finish. This has already been rendered. This is something that can go so quickly that you can actually build this and show that it just has very little latency. You're not able to discern the latency that it has. So I actually worked with Matt at a company called Interval, and they built this out of FPGAs. And it's amazing being in you put on the helmet, you have the little goggles in front of your eyes, and to be able to be in this thing and be able to move your head and so on, and have no lag, no latency, is just really a totally amazing experience. So it's certainly the lowest latency device that anybody had built. So it's a really smart thing to be able to do. Now the issue is, though, if I'm standing here, and I move, then I have to recalculate that. And there's going to be latency associated with that. So it's particularly good for when you turn your head. But it turns out turning your head is sort of the thing we're most sensitive to. So kind of the only video game that I've ever played seriously was Quake. Right? Great game. So Quake had the feature where if you unplug your network cable from your Quake machine, and you're playing on some sort of server and you're playing against other people, you couldn't move anymore, but you could turn. Okay, you can turn your head, and the reason is because the Quake designers knew that the really important thing for you in terms of not getting sick is rotational latency. That's much more important than physical latency. If I say start moving forward and it takes half a second for me to start moving forward, that's okay. That doesn't make you sick. But when you turn your head and your view doesn't change, that does make you sick. As people, we're really sensitive to this rotational latency. So this happens to be really good at rotational latency. Okay? Because if you're in one place, then you don't have to re-render it all the time. And so what the paper described is not only how the whole system works, but he said, I only have a finite amount of resources to do this. What I'm going to do is I'm going to render things that are closer to me more often, and maybe background things that I'm not going to render as often. And I'll try to have sort of priority rendering for the things that are changing. So if I don't have enough bandwidth to be able to do this whole thing, which you didn't when you build it out of wire wrap boards and stuff, then at least you can prioritize the things that are the most important. So it's a really cool project, and they did some good work at Interval where they looked at sort of how sensitive we are, and that's where they came up with sort of this figure that about 10 milliseconds is what we perceive as people. If you can get latency below 10 milliseconds, then we're not going to be able to perceive it. So pretty cool results. Okay. So there's two other cool projects that I want to talk about in this, and these are things that you could potentially add to the pipeline. Okay, so one of them is by a bunch of guys from Finland, really smart guys. Timo works at NVIDIA Research now. The second one is by a bunch of other smart guys from Sweden. And so they looked at a couple different ways to sort of extend the graphics pipeline, put another stage into it to make it more efficient. And so this idea is called delay streams. And so what they said is we sort of have this stream processing model of how we're doing graphics here. And so you have an input, you do a bunch of compute on it, you get the output out. And so what they said is, all right, we're all optimized for bandwidth here. Latency isn't such a big deal. What we're going to do is we're going to put a delay stream in here where a bunch of triangles come in here, and they just sit there for a while. Okay, they sit in this big queue. They're just waiting in line, and then eventually they're going to reach the next stage. Okay? But we're going to do some analysis on this immediately. And so the goal here is we're going to take computation, we're going to split it into two parts. And the good way to explain this is how we have Tetris, right? You can be a better Tetris player if you're seeing what comes next. Okay? If you know that something's coming down the pipeline, then you make better decisions, right? You know that the next thing is going to be, the long skinny piece. Then you're going to leave this big slot for it to go down so you can knock out a whole bunch of stuff at once, right? You're a better Tetris player if you know what's coming down the pipe. So if you take this big delay stream here, okay, and you have this big list of polygons or triangles that you're going to render, B knows what's coming down the pipe. And B can make smarter decisions because it can see what's coming next. So it's a really powerful idea here. All right? And one of the goals is to avoid redundant computations. If you know something's coming down the pipe, then maybe you're going to make different decisions. So what did they actually do with this? Okay. So one of the big things they wanted to do was culling. Okay? They wanted to say, well, if I know what's coming down the pipe, can I throw out some work that I otherwise would have to do? Okay? So this is one of the big themes here. We've talked about sort of primitive level culling. We've talked about doing like backface culling kind of stuff. We're trying to throw out work that's not going to be visible. Okay? So primitive level culling, we're good at that sort of thing. Object level culling is something that games do in CPUs, and we haven't really talked about this very much. But like if I'm going to render this whole campus here, okay, I want to be smart about it, and I would like my CPU application to say, you know what, the stuff over in the silo over there, I can't see it. I'm inside a building. I'd like to not even send it to the graphics hardware. That's sort of object level culling. Okay, we can do that. The application has to be smart about it. Other stuff is there's a feature in modern GPUs called occlusion query. I'm not going to go into that, but you also have some hardware support for being able to do some culling. But culling's really, really important. So here's what they decided to do. Okay, they said, all right, we're going to do this delay stream idea. And so we're going to have, let's see, how do we do this? Okay, so someplace between the vertex and the pixel processors, they're going to put this big delay here, okay, and we're going to have a whole bunch of primitives sitting in there. And so my idea is that I am rendering the scene, and I render this hand right here, right? And so I'm going to go to all this effort and render this hand. And then later on comes this hand, and it totally covers up my hand here. Okay? Well, in retrospect, I shouldn't have rendered this hand at all. It was a big waste of time. Just, I wanted to render back to front because I have, back to front is good for transparency and so on. Turns out I rendered this hand first, and then I rendered this hand, and this hand was a big waste of time. But if I knew this hand was coming, then I don't have to render this hand. Okay? And that's what this delay stream does. I got both hands sitting here in this particular delay buffer here. And by the time my right hand reaches this visibility stage, it can say, wait a second, your other hand's already in that delay the delay bubble there. Okay? I don't have to render that hand because I know something coming up later on is going to cover it up. And the way you're going to do that is you're going to update the Z buffer back here. Okay? So I update the Z buffer here, wait for a while, then test the Z buffer. Okay? So since I've updated it here, the front hand is already in here. And then when the back hand, the first hand I rendered, actually reaches this particular state, well, then I already know that something's coming down the pipe that's going to be better. So I don't have to render the back hand. So that's just really a big plus there. Okay? And all it's going to really take is, there's some, you have to do a little bit more compute. You're distributing things, and you definitely have some memory to do this. Now, I haven't seen this ever implemented in any GPUs. I don't believe this is implemented. But it's the sort of thing that if you could implement different stages in a GPU, this would make a lot of sense.
Since compute is growing so much faster than memory, bandwidth, the delay, doesn't this seem to not scale well with the future?
Well, I mean, you're actually adding two different things here. You have to have extra compute. Okay, to be able to, compute this guy, and you have extra memory on chip. Okay, so probably the better way to think about this is we have lots more hardware to play with. What are we going to spend that hardware on, right? We get twice as much hardware every 18 months. Okay, is this a profitable way for us to use our hardware? Now, main memory is far away, and that's getting farther away every generation. It's true. But this is something that is a queue, and it's something you would certainly implement on chip. So it wouldn't take any off-chip memory, and that's something you have pretty good bandwidth with that probably should scale fairly well. So, and again, the latency isn't so important here. What's really important is the throughput, right? The whole point is to put more latency in here, right? So that's not such the issue.
Doesn't this mean that you have to be somewhat serial in the way you generate your fragments? Because let's say if your left hand came first, and then after maybe 50 more other hands, you render this one. But then your right hand came and you said, I shouldn't have rendered this one at all. Right? So there is some kind of ordering that needed. That once this hand is in the delay, then this hand must be also in the delay.
Okay. So what you're saying is, how big should this window be?
Right.
Okay, and that's a great question. Right? So obviously, if the window is really, really big, you're going to capture all sorts of stuff. Okay, you'll do a really good the eventual goal is that you render every pixel once and only once. Okay? In a real game or a real scene, you're probably going to render every pixel 2 or 3 times because there's going to be some depth complexity there and you're not going to hit everything. So I mean, I think one of the contributions to the paper that you might want to go look at is to say, how big should this window be? Okay? It kind of makes sense. Well, it might change the way people do applications as well, because if you know things are close to each other physically, then you probably want to render them near to each other in time so that they can both fit in this buffer at the same time. So the bigger the buffer, the better performance is going to be. And you've got to be a good GPU designer and a good game designer to really take advantage of that. I mean, it's a really good question. That's the proximate thing. How big do I make this, and what sort of benefit do I get? Okay, so something else they did with it. They said, all right, one of the big issues that we have is this problem of doing good anti-aliasing. And we decided that anti-aliasing is particularly useful when you're on edges. Right? You don't really need to anti-alias in the middle of a particular solid, but when you have an edge, that's when you really want to anti-alias. When we looked last lecture at sort of the pictures that we had, we said, well, the place where it looks really jaggy is on discontinuity edges. Okay? A place where you have a solid on, where there's a big depth discontinuity, meaning it's two different objects. There's sort of a seam between those. That's where it gets really jaggy. So what we want to do is we want to render this particular solid. It's made up of a whole bunch of different stuff. Okay? So we've got this big cube that we want to render. All right? The discontinuity edges are going to be the ones outlined in red. So what we'd like to do is only anti-alias on those particular pixels, the ones that are at the discontinuity edges. At this edge, we don't have to do any discontinuity. We don't have to do anything special. We don't have to supersample because this is all the same object, so it should look pretty good. The place where it looks bad is when you have like one shader here and a totally different shader here because it's a different object. So how can we go about doing that? So the way that we're going to go about doing that is we're going to have all of our edges come in here, all these triangles we have in here, and we're going to look for a particular place where we have two edges that are next to each other. What we're going to look for is two triangles in the buffer at the same time that share a given edge. So if we can delay this entire thing, we can look and say, all right, this triangle and that triangle share this edge. Then we don't have to do any special processing there. We don't have to anti-alias this edge. Okay? This edge is covered because both of these guys are in the delay stream. This edge is covered because both of these guys are in the delay stream, and so on. This guy and this guy are not going to be in the delay stream at the same time. So that's going to be a discontinuity edge, and if we don't have both sides in the delay stream at the same time, then we'd better pay extra attention to that edge. We'd better anti-alias that edge nicely. So that's our goal. And we can do that by looking for edges. We're going to have this little hash table of edges. And you can test to see, OK, is this edge already in there? If you have an edge that's already in there and you've just sent another edge in there, then you can say, OK, that's one we don't really have to worry about. So theirs had 3,000 triangles. And they said it makes sense to have a fairly small amount of triangles because when we draw an object like this, it's likely that all these guys are going to be pretty close to each other. Right? Once you specify this guy probably gets specified pretty soon. So they thought they could get away with a fairly small buffer. So these were sort of the pictures that they had. Up at the top left was something with no anti-aliasing at all. And you'll see that there's some pretty nasty jaggies around the edges. So then you can say, all right, you can make them look a lot better if we go to supersampling. And we just supersample everything. Right? So now the edges look pretty good. But if we detect only the discontinuity edges, and we only anti-alias those, and we don't anti-alias the rest, it still looks pretty good, right? This and this look really pretty similar, okay? But this probably has 16 times as much work. Or not quite 16, but a little bit less than 16 times as much work. But you're doing a lot more work to do this than you're doing this, because here you're only supersampling on the discontinuity edges. So it's a potential thing you could put in the pipeline. We talk about a programmable pipeline. Okay? One of the big benefits is, hey, I got this cool pipeline. I got all these new things I want to do with it. I know that my application is really well suited for delay streams. I can get a lot out of my game. I've written it in a way where delay streams are going to be really useful. In my pipeline, I'm going to put in a delay stream. Okay? Something you can't do with today's GPUs. But when you heard Bill and Matt come and talk about what Larrabee can do, this is exactly the sort of thing they want to enable. The people are coming up with cool ideas like this that could be done in hardware, but could just as easily be done in efficient software. OK, any questions about delay streams?
So I guess the first thing I thought about when you started talking about delay streams was in CPUs, you kind of have this delay stream thing. You have a big window and you have out-of-order execution. So is there really any advantage to doing out-of-order execution in this delay stream to say, let's say your hand's in front of a fuzzy dog and the dog's really hard to, it's a lot more processing for all the hairs and whatnot. Your hand is easy, so you send your hand through first. I don't know.
Right. So, all right. So it's a little bit different than out-of-order execution because out-of-order
there is no out-of-order execution.
Right. So it's the thing that I think is more accurate in the CPU world is that in a CPU you sort of have a pool of instructions, and you have all these instructions that could be executed at the same time. And I know it's sort of your instruction window, I think is the technical term. You have an instruction window of instructions, and in that you can pick from anywhere in that window. That's kind of what we're looking at here. I suppose it's. I like your analogy. You are correct in saying that it's a little bit different that because you don't have, it's a little bit different because you don't have out of order here. You're not going to pull something in front of something else. But on the other hand, it is that you have a large window and you can look at that whole window at the same time. Now, what I don't think out of order hardware does is it doesn't look at the window and say, oh, that's the most important thing for me to run next. Okay, it just says, okay, whatever's available, we can start running it. As long as there's something available, it'll be running. But I think that scheduling issue is a very interesting one. And that's, again, something Larrabee's saying is going to be a big advantage for them, that they can pick what to run next because they're doing it all in software. Whereas in the GPU, if you pick what to run next, it's sort of all done by hardware. I don't think the Larrabee guys have done a lot of looking at how you can benefit from that, but I think it's one of the interesting questions going forward from an architectural point of view. Okay, so I got one more sort of technique to show to you, and this is stole these slides last night from John Hasselgren. He doesn't know that I have them, so these are totally without attribution. But this was a couple guys from Sweden. They founded a company soon after this called SwiftFoot Graphics that was recently purchased by Intel. So it's probably fair to say that Intel is very interested in the technology that I'm about to talk to you about, this sort of culling stuff. So really smart guys. I actually visited them last summer in Sweden. It's really a tremendous research group that's there.
John?
Yeah?
I had a quick question about, or a comment about the, let's see, the culling part, the delay size.
Yeah.
Culling. Yeah, so maybe you could create like a watermark where if you had a lot of similar, a lot of things that were being called, you could decrease the size of the delay so that you wouldn't have to look very far. But if you were getting a lot of if you were getting a lot of varying Z's, you could increase the delay.
Okay, so I want to differentiate between here. There's no. All right. In this scenario here, okay, you have to match everything in the delay stream to everything else in the delay stream, right? Because you're looking for two edges. So you have to say, all right, this edge doesn't match anything else. So everything that comes through has to be compared. Here, you're sort of using the Z buffer to do that sort of capturing. So the question is, why would you benefit from shrinking the delay stream? Like, I mean, maybe one way you could do, to answer my own question, maybe what.
You wanted to decrease the latency.
Okay. So do you need to, is the question. Like, why would you benefit from that? Decreasing the latency. As long as you can finish it in a frame time.
Okay. I guess in that it was the case where you actually noticed that there was some latency.
Sure. So, I mean, we're not talking like, we're talking on the order of.
It's negligible this way.
Right. This is like well under a frame time, you hope. Okay, but you might say in a programmable processor, you know what, I've only got a finite amount of storage, so maybe I can use some of it for texture cache and some of it for a delay stream. Okay, well, it turns out I don't use the delay stream very much. I'll turn that off, or I'll dial it way down, and I'll use it all for texture mapping instead, okay, or for texture cache instead. So I think the idea of having adaptivity toward doing your the size of that is an interesting one, and the question is, can you profitably use the space if you dial it down for something else? Okay, so these guys were interested in programmable culling. So we've just talked about how culling is important. Everybody tries to get rid of work that is useless work. That's one of the big themes that we have here. Okay, so what they wanted to do was a new unit in the pipeline. Okay, they wanted to have a unit that went after the hierarchical depth cull. So we sort of rasterize, we do some depth culling. Then we're going to put in this programmable culling unit. Then we're going to rasterize into fragments and then run our fragment program. So let me recap just a second about this hierarchical depth cull. Okay, if you remember the way this worked, writing on board, we sort of take our screen and we divide it into tiles. And maybe this tile is an 8x8 tile. Okay, and so we have associated with this tile, with every tile, is an on-chip Z-min value and Z-max value. And when a tile comes in and it needs to be rasterized, you can compare against this Z-min and Z-max for the whole tile. And you can say, wait a second, the tile that I need to render turns out to be, I have this giant hand on the screen up there. That's awesome. Whoa. It turns out that what I need to do is, I'm rendering this tile and I go in and I look and I say, well, the maximum value of the tile that's already in there is in front of me, so I can just throw out my whole tile. Right? So you're testing against a whole tile at a time instead of against just a fragment at a time. And that's a big win, right? Because if a tile is 8x8, then you're doing one comparison and throwing out 64 things. So that helps you solve the problem of sort of the hand-hand problem. That if I draw this hand first and then I draw the backhand second, the backhand might get totally thrown out before it even gets rasterized and before it goes to the fragment program unit. So that's a big plus. So this hierarchical Z-buffer is a really big idea here. So they wanted to expand this idea. They wanted to say, well, it's really beneficial for us to be able to do operations on tiles. And so the only thing we can currently do on tiles is cull an entire tile if if the tile is behind what's already in the frame buffer. But we'd like to be smarter about that. Okay? We'd like to make programmable culling where we can throw out an entire tile based on all sorts of different ideas. And so that's sort of what I'm going to talk about here. Decide whether we're going to process the tile or whether we can throw away the entire cull. And so does it actually work? So they got real applications and ran it through, which is really cool. Like they built an architectural simulator and they figured this out. And so what they're looking at here is sort of this heat map of number of instructions. How many instructions did they run on every fragment? So this is pretty hot, all things being considered. And it took 45 million shader instructions to execute this scene. And what they found is that when they had programmable culling and they were able to throw out entire tiles of stuff, it went way down. It went to 30 million instructions. So being able to cut out a third of the instructions is really good. And so you notice it's not as hot. And the new one is the next one. OK, that's pretty cool. So how did they do this? So here's sort of an example that we want to show. All right, we have a light shader that we want to do here. All right, and so what we're going to do is we're going to take a dot product between the normal and the light, and we're going to say, is this, and that's going to give us a value d. Okay, so basically, if d is negative, then it means that our surface is facing away from the light, and maybe that means we don't render it. We only want to render the things that the light sees. All right, so ignoring any sort of ideas about backface culling, if that's my light up here, then my front half would be, d would be positive, and my back half, my d would be negative. And so we might want to, we write a program that looks like this. Okay, there's a totally legitimate, shader kind of program, and we say, all right, here's what we're going to do. We're going to calculate a value, and then we're going to kill this fragment if it turns out to not do this particular value. Right? We don't need this fragment. We know it's not going to be visible, or we don't want to render it, or we don't want to run the shader or something. All right? So this is a kill instruction that basically gets rid of fragments that face backwards. And then if it turns out we're facing forwards, then we do a whole bunch of math. Okay. So what their idea is they say, okay, what we want to be able to do is we want to kill an entire tile of fragments at the same time. So if I'm rendering a whole tile on my back here, right, I don't want to just kill to send everything through the fragment shader and kill every individual fragment. Instead, what I want to do is I want to kill the entire tile before it even reaches the fragment program. Okay, that would be great. Okay, because then we don't have to launch 64 threads. Instead, I just look at this whole tile and I say, you know what? The whole thing is going to fail. Everything in this is going to fail. If everything's going to fail, I can throw out the tile and be done with it and not even have to send it to the fragment program. So that would be really cool. So what we really want to be able to do is evaluate this dot product for the whole tile at the same time. So how do you do this? Because for every different fragment, we're going to have a different N, we're going to have a different L. So it's really tricky. Okay, it's a hard thing to be able to do. So they did something really smart. They used what they called bounded arithmetic. So what they did is for a given tile, they, instead of just having like a single value for the normal vector, the light vector, this A vector or something, they recorded the entire span of things in that tile. Okay, every possible value that's in that tile. Okay, and they have this other value here, and they need to add them together. Okay, and so they use what they call interval arithmetic to do this. And so you can do arithmetic not just on individual values like A plus B. You do arithmetic on an entire range. So it basically says if A falls between these two and B falls between these two, then it turns out A plus B falls between these. Okay, so it's sort of this worst case scenario. Right? Worst case, if I take A from anywhere in here and anywhere in here, I can promise you that it's going to be somewhere in this region. All right? So if we go back here, we can say, well, what we can do is calculate sort of the worst case dot product. Is there any possible chance any of these guys are going to be facing forward? Well, if it is, we're going to rasterize the tile. But if we can prove using interval arithmetic that we know the range of normal vectors and we know the range of lighting vectors, okay, can we prove that D is always going to be less than 0, then we can throw out the whole tile. And that would be pretty groovy. All right, so what they do is they compute intervals for every interpolated value in the shader. Okay, so every single interpolant I send down, dot product or normal vector, light vector, all that stuff, we're going to compute the interval for that. And then they run the fragment program on the whole tile using these interval instructions. So they're going to evaluate the fragment program but only on a tile. And they're not going to evaluate it using regular math. They're going to do it using this crazy interval math. Okay? So if you run this and you find out that you are going to kill the whole tile, then they kill the entire tile at the same time. Okay? That's awesome. Okay? Because then you can totally throw it out. So they sort of showed how they thought they would do this in hardware. Okay, we have all these interpolators here. They would have to have some logic here to be able to sort of put together all these interpolators to do the interval sort of stuff. They'd have to do some lookups on texture to get particular values, and texture is one of the really hard things about this. They have to do some min and max values here before. So they went through in the paper in great detail and talked about sort of the extra hardware that they would need. And they found that they didn't feel this would be an enormous amount of extra hardware. Based on what they got. So this is something, obviously, the Larrabee guys are going to be really interested in. Hey, if we could do this in software and we could save ourselves flops from this would be very, very valuable. The other cool thing they did is more on the software side. They said, well, we run this fragment program over the entire, run the culling program over the entire fragment program. Okay, except we use interval arithmetic instead of regular arithmetic. But maybe that's kind of dumb, because there's a lot of instructions that don't lead to doing culling at all. Right? If we go back here and we look at, if we look at this program here, we could say, well, we have all these other instructions here that don't contribute to this kill at all. So instead what we're going to do is we're going to divide this into a cull program and a fragment program. And they had rules for being able to do that. Basically, you throw out all the dead code that doesn't contribute to a kill. And then this is the cull program that you run. So the cull program ends up being potentially much shorter than the overall fragment program. And that can save you some time as well. So their software system totally did that for them. OK. And then here's sort of the summary. OK, they said they were able to show that they were going to get significant speed-ups based on this cull sort of idea. That they had shaders that were interesting enough that had places where they would throw themselves out. And they're getting from 1.4 to 2.1 times the overall performance speed-up just by throwing out a whole bunch of work. So I actually reviewed this paper. There's a lot of issues with how you deal with texturing, I think. And I think that's one of the hard parts. That if you're it's hard to do interval arithmetic on a texture. It means that you have to kind of look up the entire texture, and that was tough. But when you're dealing with just math sort of things, this made a lot of sense. And the fact they were able to do some real scenes with real applications that people cared about and showed wins from that was really a very powerful thing.
So the LN thing, isn't that like the diffuse lighting or whatever of a system or something? So what if there's like ambient global stuff going on? Wouldn't you not be able to kill anything basically in that system?
Well, it's kind of a toy example. I mean, it's dependent. Like if you, I could have. It's their example, not mine. So, but it, that's a way to do. But okay. This is sort of standing in as a proxy for something I'm going to throw away because it's not going to be visible. Okay? I can't say that I know this enormous amount about how people write modern shaders. Okay? Based on their results, you would say that modern shaders, though, have places where they do kill. Okay? Whatever those places are is something that you could take advantage with a cull unit. This just happened to be a very short 2-line example that makes some sense. Okay? So you're just going to have to take it on faith that the shader says what it said it did, even if it doesn't make an enormous amount of physical sense. Okay, so a very cool piece of work. I'm actually going to finish totally on time, which is good. The last thing that I wanted to talk about was this was an architecture that was done by Microsoft, and it turned out to be a neat paper that ended up failing in the marketplace. We'll talk about why in a second. This was called Talisman, so this was described in SIGGRAPH 1996. So what they said is, here's what we're going to do. We're going to have all these different objects you have to render in the scene, and so I'm going to do those in terms of image layers. Okay? Maybe for all you guys in the front row, I do an image layer just with you guys. And then I do another image layer with the next row, and another image layer with the next row. Okay? And I will render those and then have an architecture that's really good at compositing those together. Okay? So I do all those separately. But the smart thing is I say, well, you guys in the back row, you're always falling asleep. You don't change very much. I don't have a lot of flops to spare, so I'm only going to render you every other frame. Okay, you guys in the front row, you're all drinking your coffee. Will's eating his crepe or whatever it was. You guys are changing every frame, so I'm going to render you more often. And so you can have different layers in the scene that are rendered at different rates. Okay, so it's sort of this priority rendering kind of thing. So that was kind of clever. Another thing they said is that when I have an image layer, okay, even if it is changing, maybe I don't have to change it every frame. I can say, well, you guys in the back, you're so far away that you're moving and everything and you're happy, and so the way I'm going to do that is I'm just going to take that layer and I'm going to warp it a little bit, or I'm going to move it a little bit, but I'm not going to re-render it. Okay? Instead, I can have an affine transform. I can make transforms on these images and basically treat it as an image-based rendering sort of idea. That now I'm manipulating images instead of having to re-render from geometry every time. So, and it had a lot of compression sort of stuff, so there's some really clever stuff there. The place where this ended up falling down was that they designed a system that was, this is in 1996, this is sort of the age of the new GPUs, so lots of vendors are making GPUs, and so they thought this was great, we're going to get into this. So the design they had would have taken 5 chips to implement. So they had 5 different companies that were all like building 5 chips, and they were going to put them together into this one system. Now, that sounds kind of silly to you now because every GPU is kind of a single chip now. But that wasn't really the case back then. Nobody knew how big these graphics cards were going to be. Is it going to take 5 chips to get great graphics? Will people buy something with a 5-chip card? Unclear. So Microsoft felt at the time that this was going to be a viable business proposition, that they were going to have awesome graphics, and it was going to look great, and people were willing to pay for 5 chips. Okay? Turned out that they weren't. It turned out that that was a big engineering effort. This was going to cost a lot more than some of the newer chips that came out that were like single or 2-chip kind of solutions. So business-wise, it didn't really work out very well. But in terms of an interesting system, I think it was really pretty cool. It was a neat design, and those were some good ideas there. And they made some technical decisions that maybe weren't the smartest thing, but it was definitely a very an intuitive thing to do. Okay, I'm finishing up right on time. I'll see you guys on Thursday.